Good evening, everyone. So, welcome to the sixth webinar of the National Webinar Series titled Climate Smart Sri Lanka. So, this series is organized by Sri Lanka Technology Campus under the guidance of our Vice Chancellor, Professor Chandrika Vijayaratne. And also, we are honored to have the Institute of Environmental Professionals Sri Lanka as our strategic partner in this initiative. So, with the collaboration of IEPSL and SLTC, we are leading this national webinar series. So, we would be moving to the session today, which is titled Machine Learning and Disaster Preparedness. And the session today is conducted by Professor Upaka Rathnayake from the Department of Civil Engineering and Construction at the Atlantic Technological University, Ireland, and Dr. Namal Rathnayake from the Advanced Institute of Marine Ecosystem Change and Japan Agency for Marine Earth Science and Technology, Japan. And the session would be moderated by Dr. Charitha Dissanayaka, a senior lecturer at the Department of Civil and Infrastructure at SLTC. So prior to starting the session, I would also invite you all to actively engage with the session today, and we would be opening up the Q&A forum throughout the webinar. So we welcome all the questions that you would like to ask from the panelists today, and the moderator will be accommodating those questions for you. So to guide the important discussion today, Dr. Charitha Dissanayaka would be moderating, and I would like to invite him with a formal introduction. So Dr. Charitha Dissanayaka is a senior lecturer and the head of the Department of Civil and Infrastructure at Sri Lanka Technology Campus. He is also a coastal civil and environmental engineering professional with over 10 years of experience in hydrodynamic and tsunami modeling, flood risk assessment, and climate resilience planning. Dr. Dissanayaka also holds expertise in high-performance numerical simulations, sediment transport analysis, and hydrology and hydraulic design for large-scale coastal and river infrastructure projects, both locally and internationally. He earned his PhD in civil and environmental engineering with a strong record of published research at applied work on eco-DRR and hybrid defense solutions for climate risk mitigation, adaptation, and enhanced coastal and riverine disaster resilience. So Dr. Charitha Dissanayaka would be opening up the forum and would be eventually introducing the panelists today. So Dr. Charitha Dissanayaka, now the forum is open for you.
Sorry, am I audible to you?
Yes, Dr. Charitha.
Thank you very much. First of all, I would like to thankful for you organizing such a good initiative to address the very recent disaster, Ditwa. So, on behalf of the Department of Civil Engineering at Sri Lanka Technology Campus, I warmly welcome you to Webinar 6 on Machine Learning and Disaster Preparedness. So, as you may know, over the past decade, the intensity and frequency of extreme weather events have, reminded us that disaster preparedness is no longer optional, but it is essential. In Sri Lanka, we have experienced this reality once again during the Ditwa storm in last November, which brought severe rainfall, flooding, landslide, and widespread disruption of infrastructure and communities. Even like this highlight both our vulnerability and the urgent need for smarter, fast, and more reliable decision-making system. So this is where machine learning and artificial intelligence become critically important to predict the disasters. So first of all, I would like to give some brief introduction about this. What is machine learning? I mean, machine learning enables the development of early warning system that can analyze vast volumes of meteorological and hydrological data in real time. And unlike traditional models, furthermore, machine learning supports predictive modeling for floods, tsunamis, and landslide during the storms like Ditwa, predicting which areas are most at risk can save lives. And even though if we can convey the information as soon as possible to the people, so we can reduce the fatalities. So moreover, machine learning and AI strengthen the decision support system for emergency response in disaster situation where time is critical. So authorities must decide where to evacuate, how to allocate resources, and which infrastructure requires immediate attention. Finally, data-driven structural health monitoring is becoming an essential requirement for resilient infrastructure planning. So, as an example, sensors embedded in bridges, buildings, and dams can generate continuous performance of the data that could be deployed towards the analyzing algorithm. So then we can predict the performance and safety, whether it needed further enhancement or it needed emergency planning and initiative. So then I would like to give some brief introduction about the Professor Upaka Rathnayake, and he is the first resource person who is doing the presentation under this webinar. So Professor Upaka Rathnayake is a professor in civil engineering at Atlantic Technology University, Ireland, recognized for his research in water resource, hydrology, climate analysis, and the application of intelligent systems in environmental engineering. He has been listed among the world's top 2% of scientists by Stanford and Elsevier, reflecting his significant impact and contribution to the research. Additionally, he is a lead author for the United Nations Intergovernmental Panel on Climate Change, IPCC, 7th Assessment Report, contributing his expertise to the international climate science assessment process. So, Professor Upaka Rathnayake, over to you. Please start your presentation. Thank you very much.
Thank you very much, Charitha. So, I hope you can hear me.
Yes, sir. We can hear you.
So, I'm trying to share my screen. So, can you see my screen now?
Yes, we can see.
Okay, so thanks a lot for the kind introduction and so on. So what I'm trying to do today is to get some approach about the machine learning techniques into the disaster preparedness. So going with that, main points to discuss. I'm thinking about discussing problem formulation, then looking at the explainability of the artificial intelligence side, and then machine learning and disaster prediction. So having understood the participants are from different background and so on. So I'm trying my very best to get the action into the simplest form which is possible. I'm not going into the depth of the analysis and so on because this is not a technical presentation. So let me go into the problem formulation. Now, Charitha gave a very good introduction about machine learning. So let me start with the one and twos of machine learning. See, I would like to take you to the childhood. I'll take the point option probably. Take to the childhood. So think about colors. If when you were probably at age at 1 or 2 years old, so you can't really recognize all the colors in the world. It's the same for animals. It's the same for the animals. So whenever you go into your childhood, say at 2 years old, when you were able to talk, if you see an animal, you probably say it's, okay, I'll take the local language, okay, baua. If you see a cow, you would probably call a baua. If you see a cat, it would be the same. But with time, we are trying to understand the different features of these animals. Okay, so when you grow up, you understand these features, and say in a couple of years' time, you recognize, okay, this is not a cow. This is a dog. This is a cat. Now, further into the details, you probably understand, with time, this is a bull, this is a cow. So you try to learn these features and keep them in your memory. Okay? Then recall them whenever you need. Now, that's the same thing for colors. You try to learn this. This is black. This is green. So you learn these and you keep them in your memory. And whenever you need, you recall. Whenever you see a certain color, you can recall these colors. To be frank with you, sometimes I really don't know most of the colors. Even I ask from my son to tell what's the name of this color. For me, if it is blue, it's blue. I would probably say light blue, dark blue, and blue. It has so many varieties of blue. So you try to learn them and keep them in your memory. Now, if you ask me what is machine learning and so on, I would give you these two examples. Now, you do the same thing. You do the same thing using computers and packages. So Namal is one of the very best to explain these things. But again, I'm trying to get you into the forum to explain machine learning. So you try to learn from what is available. Okay, you try to learn from what is available, and then use that knowledge to think for the rest of the things. It can be a future prediction, it can be a future forecasting, and so on. Okay, now I'll take you to further actions. So machine learning and problem formulation. I thought this is going to be very important section when you think about machine learning. Now, many people think that anyone can apply machine learning algorithms when they have data. Now, in fact, my own colleagues, sometimes who are at the highest level of their research, might think, or may have they have talked with me and they said, okay, you have data, why don't you apply the machine learning models and algorithms? Now, unfortunately, this is a very big misunderstanding. You can't do that. Yes, it is data crunching. Yeah, this is the word that they use. Most of the people think that machine learning is data crunching. Whenever you have data, you can develop models. Yes, it is data crunching, but now this is important, with a purpose. So you need to get this purpose correctly to develop the machine learning models and so on. Therefore, physics-based problem formulation is necessary. So we need to know the physics behind of the problem, then only we can develop successful applications in machine learning. So prior understanding of the problem is therefore extremely important, rather than playing with data. It's not just playing data. So we need to understand the physics behind on each and every problem. Then only we should be able to develop a successful application from the machine learning. Let me take you to a problem example. So I thought of giving you an example because many people have misunderstood this. So I thought of giving you an example application. Now this is nothing about disasters. Okay, so to get your interaction correctly, so I basically thought of getting you to a situation where I'm more interested in constructing a weir Okay, constructing a weir to develop a mini hydropower station. But I know a particular river, but I really don't know the flow which comes through that river. Because at the end of the day, this flow matters to the construction of the mini hydropower plant. Then, on top of that, that will generate my revenue. So if I'm making a profit, that is my expectation. Now, constructing a mini hydropower plant is not for anything else but to make profit while you are doing, yes, renewable energy sources, while you are encouraging renewable energy sources. So I really don't know about the flow. Now, in order to get the flow and power generation, from my physics, I know the power generation. Hope you can see my pointer movement. Can someone, Charitha, if you're there?
Yes, sir. Yes.
Can you see my pointer movement?
Yes.
Okay. See the power generation. Now, from my basics, I know power generation is, if you have a turbine, the efficiency of the turbine, which is given by eta, density of water, which is given by rho, G is the gravity, H is the head or the height. We'll say, for the simplicity, for the understanding, even though it is not the perfect way of expressing it. So H is the head, or we can say the height from the turbine to the weir. Then Q is the flow. Now, for our applications, if we say eta rho G, that is the efficiency, density of water, gravity. Let us say they are constant. Then our equation simplifies into a constant, which we can say K, H, and Q. Now, if I fix my location to have this a turbine and weir, I definitely know what is the height difference. So H is known as well. Now my power generation is dealing with Q. Q is the discharge of the river or the flow of the river. Now we all know that this river flow changes from time to time. Whenever you get storm periods, like for example, floods, which we are talking, this Q varies. Whenever you get dry periods, Q, becomes very low and low. So we can write this particular problem as a mathematical function. I'm using a subscript T here. T, power at different times, is a function of the flow of the river T. So we can develop a mathematical function like this. Now, if I basically know the Q flow of the river, I can come back to this equation and back calculate the power generated. So if I generate 4 kilowatt hours, 3 megawatt power plant, I'm selling that. I'm selling that to the customers, and I know how to do my accounting and maths, so I can calculate the revenue for me. Now, how do I find this Q, the flow? Now we may think that it's easy. We can measure the flow to a time series. It's like this. So you need the flow through a time series. That means you're not just looking at flow today, yesterday. It has to be in a long time period. So what we can do, we can measure the flow. Okay, we can measure like this. So you have, you have instruments to do measurements. But if you are doing that measurement, you daily have to do that and get the Q against time. So, for example, you probably need at least 1 year of data for this particular case. Why? Because we have in Sri Lanka, we have seasons, monsoon season, like 2 monsoon seasons and 2 intermonsoon seasons. So the flow varies with these seasonal impacts. Now, that's one way of looking at the problem. Then we can use physics-based models. So the simplest case, I'm not going into the technical details, I'm just mentioning them. So rational formula, which you probably can use, Q is equal to CIA and so on. So you probably calculate. Then we have SCS curve number method, another way. And we can go to higher levels of computational models like HMS. I'm not mentioning most of the commercial softwares here, but freely available one which I'm stating here. So you can develop a proper hydrological model and find the Q. Now, to measure the flow, we will notice that it is time consuming and it is money. It is cost because you every day have to go there and measure the flow. That's time consuming. And also you can't go every day. Then if you look at simulating flow, you need loads of data, because if you think about a catchment like this, catchment stands for the basin where we get rain to that basin and flows into this particular river. So if we are to simulate that, you need loads of data, because when we look at the catchment, it has different soil parameters, different land cover and land use. So you have to encounter everything. Now, this is again going to be a tedious task. Now, that's where we can think of the applications of AI or the machine learning into the problem. Now, we still haven't developed the problem. Now, from my basics, again, I know river flow is a nonlinear function of rainfall to the catchment. Okay, so the rainfall to the catchment. Then I have evaporation, or you can say evapotranspiration. I have groundwater recharge. Okay, groundwater, I'm sorry, this has to be recharge. A groundwater recharge. And we can have many other factors. So I can rewrite my mathematical formulation. The river flow is equal to a nonlinear function of these parameters. Rainfall, RF stands for rainfall, E for evaporation, I for infiltration, alpha for any other parameter which I'm interested in. Now, look at this. I have taken the time series. T is for time series, and I stands for number of stations. So I might get, even if you think about a small mini hydropower plant, you probably get at least 3 to 4 rain gauges inside that. Now I can rewrite this formulation like this. See? So I know power was a function of flow. Flow is a nonlinear function of these parameters. Now that is from my basic understanding of the problem. Then I can write the power is again another function of those parameters. Now this is what we call the problem formulation. Now, when we are thinking about application of machine learning into that, I need data for that. Now I'm taking you back to my very basic problem here, identifying animals. So if I don't see, if I don't see a dog and at all, I won't be recognizing it. If I don't see a cat in my life, I don't know how cat looks like. So I can't really recognize it. Similar to that, I'm coming back to our engineering problem. Similar to that, I need to have these data available with me. And not just data, I have to have solid quality data. Now, that is a tedious task. So if I have the data, I can formulate the problem into this mathematical formulation to a matrix problem. So I have, this is what I'm interested, the flow. I can have number of data. There is here, say a column, say a 1,000 data points. With respect to that, I can have these data points like rainfall at location 1 at time 1, rainfall at location 2 at time 1. Then I have infiltration at location 1 at time 1. So you can go down, you probably have here rainfall at location 1 at time n. So I can get a matrix like this. So I'm developing this matrix inside the machine learning algorithms to find this Q. So in order to do that, I need to have known values of this, known values of these, okay? Known values of this and known values of these. Now, whenever I have very good data, accurate data, I should be able to make a much enhanced or improved model. So that is how we develop the problem. Okay, that is how we basically develop the problem. So it needs much information. I highlighted much information, more theoretical background to develop a problem in the environment of artificial intelligence or machine learning. Now, I have taken a very simple example. You can take thousands complex scenarios, complex examples, and so on. Then you can develop the problem. Now, if I can develop this problem, and if I can develop the function like this, so whenever I know, say, for example, future rainfall data, can we get future rainfall data? Yes, we can get future rainfall data. I'm not saying that they are the perfect, but you can get future rainfall data for until 2100. So year 2100, you can get rainfall data. Okay, there are ways to get them and modify them, like correct them according to the location, according to the various other factors. There are some other ways of doing that, but in principle, you can get rainfall and all other climate data. So that is very possible. Now, if we know the rainfall and these information, the X or the independent variables for, say, 2040, in year 2040, if you know them, you basically know what is the flow in year 2040. So having said that, if our mini hydropower plant is going to be there until 2040. That means we know our power capacity by then. Now, this is a prediction, guys. This is a prediction. So if we know the power generation by then, we can do our maths now and we can see that is it going to be a profitable or worthy investment for me. So that's the whole idea of my first section. So I'm trying to explain the problem formulation part. Now, when it comes to disaster predictions or preparedness, it would be the same. You have the same basic, but in a different problem, which I'm going to talk with you after say 5 minutes and so on. Now, if you look at this nonlinear function pi, I really don't know what it is. The machine just gave me, or the computer algorithm just gave me those that. How would I trust it? Because even though we put some data points into the computer and say machine learning algorithms and so on, they gave you data, they gave you some answers, but I still don't know. As researchers and so on, we don't like to trust these guys because I can't see anything here. What is this pi? I know these rainfall, evaporation, infiltration, and other parameters, flow, and so on. I know about matrices and so on, but I really don't know this guy. This is the nonlinear function. Now, if you look at this artificial intelligence or machine learning approaches way back in 1990s and 2000 and so on, you probably call them artificial neural networks and so on. You had this black box guy. We call this a black box. Okay, we give inputs and we get output. As you can see from here, we give input, we get an output, different types of output. What is happening inside that, which we don't know? So there is a critical issue in this case. So many AI models back then, say in 2000, 2010 and so on, they were complex and opaque. So you can't see what is happening inside. So it is hard to understand how input leads to the output, which we don't like. See, if someone asks me to trust a ghost, I don't trust it until I see it. Just like that. So we need to find the mechanism going inside this to trust the outcome. For example, I'm taking one of my students' paper published in 2020. It's a good paper. So we predicted the paddy yield in Sri Lanka. Okay, we predicted the paddy yield in Sri Lanka with respect to the climate parameters. So we thought of doing that because we were interested about floods and so on, and due to the rainfall event, due to the drought seasons and temperature and so on, the paddy yield is changing throughout the time. Now, still we couldn't find a solution in Sri Lanka for paddy because every day we say that we are like saturated with paddy. Then again we have to import it and so on. Forget about those things. So we try to develop this particular mathematical formulation. Now, back then we used a very simple machine learning algorithm. So we had, you probably see these hidden layers and so on. So actually, we were able to get actual yield versus predicted yield. So we were kind of successful, 85%. Our prediction model was kind of successful for 85% of the prediction capacity. So we use rainfall, wind speed, minimum and maximum temperatures, evaporation, sunshine hours, and so on. We can say that it's a good fit by then, but we only know these guys. We really don't know what this is. So finding that is our next small topic, which we call the XAI. So now by looking at this problem, I probably be thinking about, and I trust our AI decisions. Now, many people do not still want to trust AI decisions. I'm not saying that you have to trust it, okay? Having said that, I'm not saying you to trust AI decisions, because we humans are much better than AI, that's for sure. So how do I answer this customer complaint if someone asks, how did you get that? So how do you answer that? So how do I monitor and debug if there is an issue? Is this the best model that I can be built? Are these AI systems like decisions are fair enough? So when you have this black box nature, you can't really get answers to these questions. So to overcome that, we use the explainability. Why explainability matters? It builds trust between human and AI. So supports ethical and fair decision making. And it enables debugging and model improvement. Finally, sometimes when you talk about AI approaches and so on, you need some regulatory compliances and so on. For example, GDPR. GDPR is General Data Protection Regulations in the European Union, Data Privacy Act. So they are at the moment discussing about getting some regulations to the AI usage. Now, in world, you probably heard about these things. You have various, how would I say, regulations, limitations in AI applications. You can't use AI for this and that and so on. Okay, now, so the explainability of AI comes into the action, which we call XAI for the easiness. It's a set of processes and methods that allow human to use, comprehend, and trust the results of the machine learning models, the results driven by the machine learning algorithms and so on. So in this era of machine learning, we are not looking at black box models. We have moved from there to look at the explainability. We are trying to explain the machine learning models and so on. Okay, now with that, I think I covered the basics of this application. So I'm moving to the exact topic now. So the machine learning and disaster prediction. So I'm taking several case studies to you from the world. Okay, I'm taking several case studies from world, which are recently published. Now, if you look at this particular paper, it was published in just a month ago. Okay, just a month ago, 2026, in Journal of Hydrology Regional Studies. Now, so Yusufi et al., they published a paper which is on reinforcement learning approach with explainable AI for spatial flood susceptibility analysis and so on. So what they have looked at to a particular catchment in Iran. Now that is the catchment which they have invested. They developed the flood maps. Okay. Now these flood maps you can develop by the very basic concepts. So if I go back to my previous slide, you can develop flood maps. You can develop flood maps, not definitely by HEC-HMS, but you can use some other softwares like HEC-GeoROS. HEC-GeoROS. These are computational packages where you can develop inundation maps and so on. But it needs loads of data and so on. So now I'm taking you the example again. So they have developed some flood maps using machine learning algorithms, and they have even used explainable AI to build the trust of the users. Now, as I told you, this was published in one of the very best journals in the world, that is Journal of Hydrology Regional Studies, because it's more related to region, so it was published in Regional Studies. Okay, let me take you to the case study approach. Now, what they have done, they sorted some initial variables. Again, I'm not going into the technical details, all right? So they sorted some initial variables based on the physics. And they looked at a Pearson correlation coefficient, which is a linear coefficient. So, yep, there are some issues of looking at it. But again, from the basic physics, we can argue that these are the nominated variables that they are going to look at. So they looked at these variables. You can see how many variables they have looked at, 22 as I can see. And then they develop the machine learning flood map prediction model. So the model is based on machine learning algorithm. So they use training, test. What do you mean by training and test? Now you remember the example of our animal selection. So you train your brain. Just like that, mimicking that, you train the machine learning algorithm. Using 389 data sets, then that trained model has to be tested for its accuracy. So they used 156 data sets. Now, these are massive data sets, guys. These are basically massive data sets to test their development. So they used several machine learning algorithms, and this is how they have selected the best from the performance. As I told you, you have to test them. And they selected the top performing model, and they checked for the XAI. That's the local and global explanation. Again, I'm not taking you to the hardcore of this explainability, but you can check the global, local explainability. For example, use LIME, LIME, SHARP, SHAP. Then you can use PDP plots, different ways of looking at this explainability. So they looked at the explainability, and they rank the variable. Now, what do we mean by ranking the variables? Among these nominated variables, there may be some particular variable which is really impacting the solution. Okay, now if I take you back to this particular example which we discussed about the power generation, I definitely know rainfall has to be the impacting variable, because rainfall directly impact. I mean, the influence is high to the flow. Yes, there is an influence from evaporation and infiltration, but yet rainfall has a major impact. So we know that from our physics. So that we can say. But when you come to a very complicated problem like this with 22 variables, you can't really get it from physics. Even though you can get it, it would probably need a lot of time and so on. So you can rank the variables. And also, if you see this particular arrow, they developed the flood susceptibility maps. Now, taking you to the results from them. Now, this is the particular catchment they were looking at. They have identified different areas of the impact of the floods. See, if you look at, I'm just taking one example. Okay, if you take this particular example, you have very high level. See, very high level. So these are the levels or the areas which can be impacted due to a flood and this basin. Okay, now that is my first case study explanation of the machine learning approaches to disaster preparedness. Now, why I say disaster preparedness? They just developed some flood maps. Is that enough? Now, these flood maps can be used for future planning of cities, planning of residences, and so on, which we are missing. Okay, I'm taking my example for another case study with droughts. Now, when we were kids, we used to say that Sri Lanka is away from these disasters and so on. We don't have any disasters in Sri Lanka. That's what we used to tell. But unfortunately, we have loads of incidents coming on at the moment, and we can see these disasters. Again, sometimes we debate about natural disasters or human or man-made disasters. Even it is a debate in the United Nations whether we should call natural disasters anymore or not, because all these disasters are kind of human-made. So we are debating about using a natural disasters now. Nevertheless, we even have experienced bit of droughts to Sri Lanka. So my second example is about droughts. Now, this is in scientific reports, which was not published, Nature scientific reports, which is not published yet. As you can see, it says article is in press. So one of the very best journals in the world. It's the top 5th journal in the world, I think, Nature scientific reports. So it was just accepted to publish in scientific reports. And what they have done, they have basically looked at drought class prediction to a catchment in I believe it's in India. So look at the way data collection, data pre-processing, feature selection, the fundamentals are still there. So I'm taking you to the next, and these are the subclusters they define, like no drought to drought, extreme drought. They have categorized them D0, D1 to D4. So you have various definitions for these things. For example, D4 is extreme droughts and so on. Irrigation system fail and so on. Now, they predicted the drought conditions and the catchment, as you can see, drought level distributions, and they looked at the accuracy of the prediction model. Finally, the predicted droughts are used to develop a robust tool for early warning systems. Now, if you look at the application that's to Sri Lanka, we probably look into the staple food in the country. So if we can predict the drought levels, now that's a disaster. That's a disaster. So say if we are in D2 in the coming year, so you can get prepared for that rather than just telling things in news and so on. We are good at this and that and so on. So saying we have the world best irrigation system. Use the scientific evidences to escalate these issues and get the early warning systems or the decisions. I'm taking you to the, with time available, I'm taking you to the third example, which is again heart-touching to Sri Lanka after the cyclone Ditwa. So the landslides. Can we predict landslides? Again from our neighbor, Sri Lanka. So these people, Mandal at Saha, in 2026, for this particular area, which is at the northern India, they develop a deep learning approach, which is based on GIS, landslide, again for prediction of landslides in Himalayas. So as you can see, they have obtained a lot of information. You probably can see them, and they have used satellite images, which are freely available, obviously, and develop the model using deep learning approaches. And the outcome, okay, the methodology of this particular work shift is like this, which I obtained from them, their people. The outcome was superb. Now they have developed the prediction maps using different algorithms. Not only that, they have ground validated them. If you can see, they mapped their prediction to the existing landslides after some time. So this is a fascinating work. So that means we just tell the prediction of landslides. Say we can have a landslide in this particular area. Yes, we can do. Yes, we can do that. Even if you look at the last couple of months, when I read the news, I understood that the authorities sent messages and so on, saying that we are getting 100 millimeter above rainfall or 200 millimeter above rainfall. So these central hills are there to have some landslides. So we need to evacuate. Yes, but you can use the science. You can use the latest technology, which is readily available, to predict exact locations and exact amount of these landslides. And people have done that. So I'm taking again a bit to some insights. Now this was done by one of my former students who is now doing his PhD. So Makumra Randika, and he's originally from Sri Lanka Technology campus. He did his bachelor's in civil engineering in UU Institute. So he's doing his PhD now here in Atlantic Technological University. So he developed a model to gain catchment in India. Not only he developed the prediction model for stream flow, forecasting model for stream flow, because this was I can say it was an interesting catchment because you have groundwater a lot. groundwater flow a lot. So developing the model was not easy. But at the end of the day, we were able to develop a digital platform, just like a mobile phone app. Okay, mobile phone app to get the details. So the flood levels and so on. So this is possible with the latest technology. Okay, now hope you understand a bit about the approaches in machine learning algorithms or artificial intelligence with different words, you know, into disaster preparedness. Now, my questions to you: what we can do for Sri Lanka? Now we have observed or we have experienced a lot of floods. Are we going to experience more? As per the United Nations IPCC 6th report, now that is the available report at the moment, Sri Lanka is one of the most impacted. You have the rank in the report. Sri Lanka is around 2 or 3. So that means the second or third most impacted country in the world from climate change. Now, this impact would not simply come into the rainfall. It would come into the agriculture. Because we have 23 million, 22 to 23 million population. We have to feed them. So we can't always say that we get donations or whatever the things from other countries. Like we have a staple food, which requires massive amount of water, paddy. So we basically have to look into the climate impacts to each and every area. So floods, definitely we need to predict. Not only floods, now adjoining disasters like landslides. We lost, I don't know the exact number, but we lost more than 700, 800 people because of Cyclone Ditwa. And if you look at after disasters, like, when you have these floods and so on, it is natural to have various other spreading diseases. Can we predict them? Can we identify the hotspots of these spreading diseases? Then the other way around, droughts, can we predict them to Sri Lanka? Agricultural damage. It's not just because of the climate change. Can we do it to wild animal damage? These are some set of questions for you to think. Now, as a final note, research itself is not enough. Trust me, you can do research and you can publish 1,000 research papers. It won't help. So, for example, I can say that, okay, I publish in this particular journal. It is a world-based journal and I'm happy about it. But can we really be happy? Now, this research, we have to develop the related policies from the research outcomes. Then we have to implement them. If you are not implementing these research outcomes as policies, okay, you have a paper, you have some sound research projects, and you got outcomes, it's there. Still, when we get another disaster, we are the same. We need to beg for the things from the world. So, as I told you, research itself is not enough unless we develop related policies from the research outcome. So, this is what I wanted to talk with you today. So, I believe by understanding the audience and the attendees, I haven't gone into the depth of any technical terms. Beg your pardon if I had. So, yeah, Charitha, that's all from me.
Thank you very much, Professor, for your insightful session. So next we will move to Dr. Namal Rathnayake. So first of all, before begin the session, I would like to give some brief introduction about Dr. Namal. Can you hear me?
Yes, I can. Hello, can you hear me?
Yes. Sorry, Doctor. So, Dr. Namal Rathnayake is a distinguished researcher and educator specialized in artificial intelligence, machine learning, and environmental modeling. He is currently serves as a researcher at the Japan Agency for Marine Science and Technology, contributing to the World Premier International Research Center Initiative, Advanced Institute for Marine Ecosystem Change. Then he holds a PhD in computer science from the Kochi University of Technology, Japan, where he developed the novel Cascade Adaptive Network-based FUSI inference system algorithm. His research expertise lies at the intersection of AI and earth sciences, especially in leveraging deep learning and data assimilation to optimize weather forecasting and enhance disaster preparedness. An accomplished academic, he has authored over 35 peer-reviewed journal publications and has been recognized with prestigious honors including Sakuma Award for International Research Excellence and multiple Kanken research grants for his work in rainfall runoff and flood prediction. Beyond his research, Dr. Rathnayake has extensive experience as a lecturer and consultant, mentoring the next generation of engineers and collaborating with industry on robotics and autonomous systems. So, Dr. Rathnayake, over to you. Please start your presentation. Thank you very much.
Hello, everyone. Can you all see my screen?
Yes, we can see your screen.
Okay, thank you very much. Good evening, everyone. And thank you very much for inviting me to the session. And we had a really good session before me, Professor Upaka Rathnayake, where he introduced how we can actually use this machine learning into the systems, like in theoretical manner. Like I have a little bit of theoretical and also like practical, and also like show what kind of applications that we can use machine learning for. So first of all, I welcome you again to the 2026 National Webinar Series, Climate Smart Sri Lanka, from Awareness to Action. It's very nice. My name is Namal Rathnayake from Advanced Institute for Marine Ecosystem Change in Japan. So in this part of the session, we are focusing on exploring a critical frontier for our nation, like how we move machine learning from purely academic research into frontline tool for climate disaster preparedness, because we have done so many things, and then we like to see that how it is going to be applied in the application wise, and how it can help our country and so on. So let's move on. So yeah, we can begin with these images, because they represent the current reality for thousands of Sri Lankans. So as climate patterns shift, we are seeing an increase in flood frequency and intensity. So these are just statistics. They are disrupt livelihood, urban centers brought to a standstill, and a growing challenges for our disaster management infrastructure. Right. So currently, our responses are often reactive. We act after the water rises. So our goal is to shift that paradigm towards predictive action. So why do we need a new approach? So that's the question. Historically, we have relied on traditional hydrological models. So while physically sound, they are often data hungry and computationally slow. So in a crisis, time is most precious resources. You can remember this, right? So in Sri Lanka, faces specific challenges of data scarcity in many reverse basins. Like Professor Upaka and me and our research group has a really good experience with this data scarcity in Sri Lanka. So how we struggled when we try to do some researches for Sri Lanka. We'll not talk about it. So we need a system that are adaptive, model that can take limited local data and provide high accuracy, real-time forecasting to give our decision makers the intelligent lead time they need to save lives and property. So that's our target. So moving on. This brings to the core of my research journey. Actually, here I will explain a little bit about myself, like how I am engaged in disaster management type applications and so on. So it all begin in 2020. Like I joined Kochi University of Technology for my PhD in computer science to solve real world problems. So in 2021, we fortunately were able to introduce a new algorithm called cascaded ANFIS to handle complexity of environmental data. So by 2022 and 2023, we began to apply this logic to specific Sri Lankan challenges, not only Sri Lanka, I will explain it to you later. So like hydropower forecasting in Samanalavawa, starting from that, and then flood prediction and Malwatuya and Mahavali rivers and so on. So in 2024, 2025, we expanded our scope to multi-hazard systems like encoding air quality, like PM10 forecasting and forest fire spatial mapping and so on. So throughout this journey, the mission has remained the same, like using AI to transform Sri Lanka's climate awareness into life-saving actions. So if the traditional models are too slow, what are the alternatives? So that's a question here, because we already have the traditional models. So let me briefly introduce one of my core methodological contribution, the cascaded and adaptive neurofuzzy inference system, or we can say cascaded ANFIS. I'm sorry. In this few slides, I will explain a little bit in detail, like theoretical, but also I need to explain like why this model performed really well and why we applied this model to many of the applications in Sri Lanka. So this algorithm is an extension of ANFIS that was introduced by Professor Zhang in 1996. It's a very old one, but then we were able to give a new birth to the ANFIS algorithm called cascaded ANFIS. So the traditional ANFIS is powerful, hybrid, a neural network and a fuzzy logic combination. So it combines learning capability with interpretability, which makes it very attractive for nonlinear optimization problems. Professor Upaka also talked about explainable AI, explainable artificial intelligence. So this fuzzy logic itself is very explainable to human. Like fuzzy logic itself is a human-like logic. So instead of using the deep learning models or some other machine learning models, like if you use fuzzy logic models, you know exactly how the output has become like that for the corresponding inputs. So we are using this ANFIS model, which is a advanced version of fuzzy logic, and then it has two major, like if you talk about ANFIS model itself, it has two major weaknesses. First one is, we call it curse of dimensionality, which performance degrades when the number of input variables increases. So if you are talking about environmental modeling, you know, like how many variables that we can have. So for example, I had a postdoc in University of Tokyo where I was doing modeling for cyclones. So I tried to track the cyclones and try to predict the cyclone intensity. So to track the cyclone intensity and find the path of the cyclone, I had to deal with this huge cubic of data. Like the variable size is around 10 to the power 50 around. So we cannot actually use that amount of data if you are using fuzzy logic based, like ANFIS based algorithm. So that's one one problem we have, like curse of dimensionality. The second one is like computational complexity, because the more the training becomes very expensive as the model grows. So these two problems, to address this, we propose a novel architecture called cascaded ANFIs. So the key idea is simple but very powerful. Like instead of feeding all the input variables into one large ANFIS model, we use a small 2-input ANFIS as a base unit. So if you just search for this algorithm, you can find our paper, and it has all these methodological steps, like how we have developed this one. And it's very interesting. Even if I read it right now, like I can't even believe that I was able to be a part of that. So we use a small 2-input ANFIS as a base unit, and then pair selection mechanism, evaluate combination of input variables, and then output of one stage becomes the input of the next stage in a cascaded manner. Like it's very interesting. So then the output, like the iterative refinement narrows the error progressively. So this structure allows us to handle the high dimensional data sets while keeping the computational complexity stable, because at a given time, the model only process 2 inputs at a time. So I highly suggest like read the paper. It's really interesting. So this algorithm, you can forget about that. So we have this algorithm right now. It's called cascaded ANFIS. We use that algorithm to find its capabilities, try to find the limitations of it. So the one thing, we evaluated this on 7 publicly available dataset ranging from 4 to 561 input features. So the first problem that I told you, like curse of dimensionality, we wanted to address that. So we tested for various input features. So compared to the state of the art, sort of ANFIS optimized with genetic algorithms and particle swarm optimization, the cascaded ANFIS consistently achieved significantly lower root mean square error and the lower MAPE and the near perfect correlation in several cases, while also reducing the training time. So it was very successful. So if you can see in these slides, you can see how the responses are with how they are aligning with the output. So in summary, like cascaded ANFIS transforms ANFIS into small scale optimization tool into scalable, high accuracy framework suitable for complex real world prediction problems. So now we have a good algorithm. So what we did was, let me now present like one of our work applying the cascaded ANFIS algorithm to simulate nonlinear rainfall runoff relationships. So hydrological modeling is inherently complex, right? Because river flow depends on multiple atmospheric and catchment variables. It's not only the river. Like many regions, especially developing countries, we face this data scarcity, as I mentioned before. Physical hydrological models require extensive input such as soil properties, geometry, and the atmospheric conditions, which are often unavailable and unreliable. We don't have many stations. We don't have many measuring stations. So this is where like AI and machine learning comes in, and our model comes in, especially. So we tested this model, the cascaded ANFIS model, on 5 rivers across 3 countries in Sri Lanka, Vietnam, and Japan, as you can see here. Especially in Sri Lanka, like Kalu and Kalani, and Thubon in Vietnam, and in Japan, it's Nyodo and Monobe, which were near to me when I was doing my PhD. So these basins were very significantly in climate, size, and hydrological behavior, making the validation geographically robust. So it's not just one application. We tried with 5 different geographical regions and 5 different sizes and 5 different climate zones. So the results were perfect. So to address this real-world problem, we developed the rainfall runoff model using cascaded ANFIS that relies primarily on rainfall data. So the architecture uses only 2 input, 1 output ANFIS as a base unit, as you can see here, and applies cascaded structure with pair selection and iterate training, allowing us to manage computational complexity while maintaining high nonlinear prediction accuracy. So Moving on, we compared our model against 6 state-of-the-art algorithms, including LSTM, GRU, RNN, linear regression, and lasso regression, and so on. So across all the basins, Cascade and FIS had the best results. So we tested with NSE, KG, and root mean square error and correlation coefficient R square. And also, Cascade and FIS had the near zero bias, which is very important. For example, like in the calendar river, it achieved like highest correlation and lowest root mean square among all the models. So the key takeaway is that this approach provides generic transferable rainfall runoff prediction framework suitable for data scarce environments with strong potential for real-time flood forecasting and disaster preparedness. So this is one application. So we also published a book chapter combining all the models that we used for with Cascade and FIS. As you can see in this slide, like the summary of the chapter that we wrote is shown. So we did a modeling for Mahavali River, where we got 21% higher accuracy in prediction compared to SOTA, and also lower bias, robust under climate scenarios, also performs well with limited inputs. So we'll talk about this in detail in the coming slides. So moving on, let's talk about case studies, like clustered case studies. Sorry. So this work is particularly important for Sri Lanka using Mahavali River as a case study. So the Mahavali River, as we all know, is the longest river in Sri Lanka, which plays a central role in irrigation, hydropower generation, and flood control. So, however, accurately predicted water level this basin is extremely challenging due to nonlinear rainfall runoff dynamics and limited high-resolution hydrological data. So we don't have high-resolution data, but we have to work with scarce data that we have. So to handle this problem, in this study, we developed a cascaded ANFIS-based model to predict river runoff and compare its performance against deep learning models such as LSTM, GRU, and RNN. So the results are perfectly clear. The Cascade ANFIS model achieved correlation coefficient approximately around 0.93, which is very aligning to the truth, outperforming LSTM and the other neural networks. Like LSTM, you know, if you are working with machine learning, like it is kind of a top tier in machine learning models, which are also low in complexity. The overall accuracy improved was about 21%, as I mentioned, like for the Mahavali River, compared to the second best of this model. So some of the results is not only statistical, actually. It means more reliable peak flow predictions, which are critical during extreme rainfall events. So importantly, like if you talk about the bias, the model also contains near zero bias, meaning like it does not consistently overestimate or underestimate flood magnitudes. So some of the, as you can see here, the Cascade ANFIS also tested with multiple SOTA algorithms. You can see how it has been outperformed, how it outperformed all the other machine learning models. When we extend the model into future climate scenario, so we did not stop just by predicting. We just trying to extend our modeling to predict the future, predict for the future climate scenarios using shared socioeconomic pathways. Some of you may know, like we call it SSPs. So significantly, we use SSP2 4.5 and SSP5 8.5. So these scenarios simulated moderate and high greenhouse gas consideration pathways. SSP2 4.5 is, I think, the best scenario, and SSP5 8.5 is the worst case scenario. So under both scenarios, the model projected changes in flood frequency and magnitude, including potential drought-like condition during certain months. So the previous one is for SSP 4.5 for near future, which is up to 2031. And this one is up to 2051, is for the mid future. So What is important here is that the model remains stable under these scenarios driven rainfall inputs. So this shows the robustness, not only for present day, but forecasting, also for forecasting and not long-term climate adaptation planning. So another key advantages in practicality, the model relies primarily on rainfall inputs rather than extensive climate parameterization. So as I mentioned before, in many Sri Lankan basins, soil data, land use data, and high resolution measurements are very limited or inconsistent. So a rainfall-driven intelligent model is therefore more realistic for operational development. We just let the machine learning model to assume those unknown parameters, and it works. So moving on, in practical terms, this research support 3 critical national priorities. First one, improved flood forecasting with higher reliability. Second one, optimized reservoir operations to reduce downstream disaster risk. And the third one, early warning systems that can be integrated into disaster management platforms. So in summary, this study actually demonstrates that advanced explainable machine learning models can move from academic research into real deployable infrastructure for science, strengthening Sri Lankan climate resilience. Moving on to the next one. So this is our second case study that I selected from bunch of that we have. Is the Malwatoya, second largest river in Sri Lanka, with the catchment area around 3,284 square kilometers. So it has experienced severe flood events, as you can see here, like in 2020, 2011, 2014, and 2016, including reservoir breaches that cause extensive downstream damages. So more than 400,000 people live within this basin, like many of them depend on agriculture. So it is very important. Accurate water level prediction here, like is not just an academic, it directly affects livelihood and disaster resilience. So traditional hydrological models require extensive climate characteristics, as I mentioned before, like soil data, the land use, roughness coefficients, which are often incomplete or unavailable, right? So this study actually is investigated whether the soft computing, gradient boosting techniques would accurately predict water level using primary rainfall inputs. As I mentioned before, the machine learning models asks to assume the other factors and try to model just by using the rainfall inputs. So how was it? So we used rainfall data from 6 gauging stations. This is how we did it. Of course, with Professor Upaka. And we used the data from 2005 to 2018, total of around 5,000 data samples. And then this experiment was conducted under the lag configuration of 1 day, 2 day, and 3 day. Like we can also say like one day ahead forecasting, 2 day ahead forecasting, and 3 day ahead forecasting. We compared with 9 different models, black box deep learning models like LSTM, GRE, and RNN, and also regression models and gradient boosting models. And the results, give me a second. Yeah. The results are actually very interesting. So as you can see here, we used several different models, CatBoost, XGBoost, Light GPM, Ensemble models, and also ANFIS, LSTM, and RNA. So the CatBoost algorithm clearly outperformed all the other models. For the 3-day lag configuration, it achieved correlation coefficient around 0.99 on the testing dataset, which is extremely high, right? So, which like, it's perfect results, actually. It's also achieved the highest NSE 0.98 and also KGE 0.95, which is with very low root mean square and NR. So in contrast, deep learning models like RNN, LSTM showed higher bias and lower stability. So we cannot actually trust on deep learning models here because the data samples are low. So maybe the deep learning models does not have enough data to find out the correct relationship. So another important observation is like computational efficiency. So gradient booster models require significantly less computational power compared to the deep neural networks. So this makes the like highly stable for real-time implementation, like resource constrained environment like in Sri Lanka. We don't have high performance computers. We also tested ensemble models combining gradient boosting algorithms with the AND phase, and they also perform really well. So this also indicates that sometimes a well-tuned gradient boosting models can be more efficient and robust than more complex ensemble structures. So we found many outputs. We had many insights from this study. The key takeaway from this study is that a highly accurate flood forecasting does not necessarily like require computationally heavy black box deep learning models, but instead well-structured gradient boosting approaches can deliver superior accuracy, lower bias, and better operational feasibility. And for Sri Lanka, this means that we can realistically deploy real-time early warning systems that are computationally efficient, scalable, and suitable for national level disaster management infrastructure, because we have proven it. So linking this to the broader theme of machine learning and disaster preparedness of Sri Lanka, the key takeaway from this study is not just model accuracy, but it is a shift how we can think about data availability. So in this study, the next study, which is about Narmada River Basin in India, we address a critical methodological gap in downstream flow prediction by shifting from conventional flow-based input to upstream water level basin modeling. So traditionally, most hydrological machine learning studies rely on historical discharge data predictors. However, like discharge measurements are often inconsistent, labor intensive, and unavailable in many basins. It's not only for India, actually. Even in Sri Lanka, we had some discussions with Disaster Management Center, and we were talking about like how difficult it is to maintain. So in contrast, like water level observations are more widely recorded and operationally reliable. So therefore, this study investigates whether daily upstream level data alone can robustly predict downstream flow at this river in Narmada River Basin. So this is the methodology. So we utilize like long-term data sets spanning from 1978 to 2020, like more than, I think, 15,000 daily observations from the data set. And then the input features consist of level measurements from 5 upstream stations, while the downstream discharge was used as the target variable. So we also train 4 advanced ensemble learning models, CatBoost, like GBM, Random Forest, XGBoost. And then the performance was evaluated using mean absolute error, mean squared error, root mean squared error, and also R squared, and so on. So I am talking about these things because again and again, we are using the same kind of machine learning models and showing that how effective they are in these kind of like different geographical regions, and which gives us the hint that we can actually use them, right? And moving on, XGBoost showed the most stable performance across all phases, which has a superior generalization capability. So in the testing phase, like XGBoost achieved around R squared around 0.96 and root mean square around 0.2, and it was the lowest from all of it. So the contribution of this work is methodological, actually, by like demonstrating that upstream level data can effectively replace discharge inputs. We established a scalable framework for river basins where flow measurements are sparse or unreliable. So in summary, the study confirms that gradient boosting ensemble methods particularly XGBoost, can actually accurately model complex nonlinear level flow relationships, offering robust alternative paradigm for downstream flow prediction. So it's not just one algorithm that works for every basins, every geographical regions, but sometimes there are several different models works for different kind of geographical regions. So like before, we talked about cat boost algorithm, and now we are talking about XGBoost algorithm. And let's move on. So going out of the floods, our primary focus is often on water, like climate disaster preparedness in Sri Lanka. Like disaster preparedness in Sri Lanka must be holistic. So air pollution, if you talk about air pollution, is a silent environmental hazard that cost lives and massive healthcare expenditures. Like in 2023, we saw unhealthy air quality index level across 5 major cities in Sri Lanka, so including urban centers like Colombo and Kent. So that's where we wanted to do this study. For the first time in our country's context, like we applied advanced machine learning to forecast PM10. That PM10, do you know PM10? It's the matter that penetrate deep into the respiratory system, and then it can also, like, if it is like, it is critical because long-term exposure can directly link to increased hospitalization for asthma or even in deaths. So our study focused on two main geographical distinct urban areas, Kandy and Battaramulla. The Battaramulla is like at the sea level with high industry activity, and Kandy is like high altitude with unique basin effects. So what happened is, like, we utilized historical hourly data for 12 variables, not just air pollutant like SO2 and NO2, but also meteorological factors like wind speed, solar irradiation, and the humidity. So because weather drives air quality, the factors are essential for accurate forecasting. So we tested 5 powerful models, SOTA models, XGBoost, CatBoost, like GBM, and also cascade analysis, LSTM and GRU. And to ensure like institutional trust, we didn't just run the models. We conducted rigorous cleaning process, removing noises, optimizing hyperparameters, and so on. Like, because if you talk about the environment later, it's always like noise. So we have to do pre-processing. So we wanted the model to react for the true data. So moving on, the results are very interesting. Like it is actually outstanding. So the across both locations, Kandy, Battaramulla, like GBM, like BGM, algorithm emerged as the best model, and near perfect correlation, and R2 is around 0.99, and both Kandy and Battaramulla regions. So talking apart from the air pollution, we also looked beyond water and air. Like, we must address our terrestrial heritage, right? So forest fire, like increasingly threatening Sri Lankan biodiversity. Recently, I heard about many forest fires in Sri Lanka as well. So until now, we lacked a comprehensive national scale risk assessment. So this is one study that we did in 2020. I'm not sure. So using a baseline, we conducted the first ever GIS-based study to map forest fire risk across the entire country. This is no longer a localized issue now. So we heard, like, recently there was one in LA as well, right? It was a huge fire and many losses happened. And with climate-driven droughts and human interfaces, like understanding where our forests are most vulnerable is a prerequisite for effects consultant. So to build this forest fire index, FFI, we integrated 7 independent parameters derived from remote sensing and GIS. These factors like included static terrain factors like slope, elevation, and aspect, and then also proximity to main roads, and human settlement where accidental ignition are most likely. And also like environmental indicators like land surface temperature, LST, and LUSLC, like land use and land cover. So we validate our model using World MODIS hotspot data, tracking 735 actual fire counts across the island. So you can see the results. The results actually very surprising and counterintuitive for some. So low risk zones are like the central and Uva provinces district like Nuwara, Kandy, and Badulla actually show very low risk due to their high altitude and the cooler temperature. And high risk clusters are districts like Hambantota, Kalutara, and Kurunegala, containing high risk densities, primarily in low altitude regions with elevated surface temperature. It is always hotter in those areas. And national studies overall 49.49 of Sri Lanka falls into the medium risk category, while we aren't currently facing an extensional national threats. We are at the tipping point actually. So we have to be very careful of this one. So for the Minister of Wildfire and the Forest Resource Conservation, this is not just a map actually, it's a decision support tool. It allows authorities to prioritize patrol routes or position firefighting resources in high risk zones, and also like design targeted public awareness campaign before the dry monsoon season begins, because no one knows where the fire can start again and destroy our lives. So moving on to the next one, like disaster preparedness isn't just about surviving floods, it's about ensuring our national system remains stable under climate stress. So now we have the problem of, in talking about energy, we have the problem with, I cannot remember, the gas. Gas is like in Sri Lanka, right? So this is about not gas, but the electricity. So energy security is a critical part of this. Like Sri Lanka aims to generate 70% of its power from renewable by 2030. That's why the government is forcing or like aiding us to install solar panels in our homes. It's a really good approach. However, the wind and hydropower are inherently unpredictable, right? Because wind, we never know if there will be wind or not. And also, we don't know when the rain will come. It's very non-linear and also unpredictable. So in recent years, our distribution network has faced total blackouts due to imbalances between demand and uncertainty generation sources. To prevent this, like what we need is like intelligent systems, right? That don't just react, but also predict. So we did the work with the Samanala hydropower project, applied the cascaded and fish algorithm to forecast generation up to the year 2099. We try to forecast how much power generation can be done with the future rainfall scenarios. So by integrating fuzzy logic with the neural networks, like we address the nonlinearity of rainfall and restoring flows. So the results you can see that very interesting. We use several machine learning models, and the superior accuracies from cascaded and fish. Minimum error is around 1.01, outperforming the best models like GRU, which is the second best is 6.5, the root mean square error. So it's perfect in the sense of results. So from cascaded and fish, what we did was we tried to predict for the near future, mid future, and the far future, which is up to 2040. You can see how the power generation is varying depending on the climate scenarios, RCP 8.5 and RCP 4.5. Then moving on to the next one, from 41 to 2099, how the power generation is changing. So this is really a good output for the policymakers and overall the Sri Lankan community to understand how the future will be. So that's all applications that I put into these slides. so far to give you some idea like what kind of applications that we can use using machine learning and how we can actually answer the question, can we really do that? So when we move forward towards like developing these models nationally, we face the critical question from our colleagues like DMC, Disaster Management Center, and the Irrigation Department. Can we trust this? As Professor Upaka also said, can we trust this? We can trust this traditionally. Advanced machine learning are viewed black box. Professor Upaka explained it very clearly. You feed the data and the answer comes out, but reason is hidden. We don't know what happened inside and why this output is there. So in a high stakes environment like flood evacuation, national grid management, and a prediction without a reason is difficult to act upon. So if an algorithm predicts a catastrophic flood, a director of irrigation needs to know what is driving that risk before issuing an order that affects thousands of lives. So if I give you an example, if you remember, when Rita comes, like opposition parties say, it is coming. The people are saying, why didn't you open the gates, right? So we cannot actually do that. We have to know exactly, is it coming or not, right? This is where like the trust is very important. Can we really trust this? So if an algorithm predicts, yeah, we have to understand why it predicts like that. To bridge this gap, we always try to use the explainable AI method, like especially using like SHAP or line methods. So SHAP is based on cooperative game theory, like it mathematically breaks down like every single prediction into like show exactly how much each input variable contribute to the final result. So gives kind of a SHAP score for each output, like for each variables, so that we know like how much of this input has contributed for this output, something like that. So if I give you some examples, like for our wind power, we did one project for the wind power in Musalpetti. The model doesn't say like power will drop by 20%. Through SHAP, what we can do is like we can see that while wind speed is the main factor, the sudden change in air temperature or turbine nozzle alignment is the specific reason for the prediction. Because like our model not only used the wind velocity for the prediction, it also used the nozzle, turbine nozzle alignments and the air temperature and the humidity and those kind of all the other environment factors as well. So if it gives a reason, if it gives an output, we know exactly how much percentage of each input has contributed for this output. So this moves us from blind faith in an algorithm to informed evidence. So let's apply this to a flood scenario. Let's talk about Mahavali River. Instead of just a water level alert, our XAI framework can tell the operator the flood risk has increased because of 48-hour accumulated rainfall in the upper catchment, even though the local rainfall is low. So where the water level is measured, the rainfall is very low, but the upper catchment is heavily raining. So this is why you get a huge level of water because of 48-hour accumulated rainfall in the upper catchment. So this kind of information can be generated, can be taken from these explainable AI scenarios. So if we use the same scenario for the air quality work, we can identify whether a PM10 spikes in Kandy is driven by specific meteorological shift or seasonal patterns. So those kind of things, like this kind of details is what makes the system climate smart. Like it provides the transparency needed for institutional leaders to make confident data-driven decisions. So moving on, this ultimate benefit is that we convert raw data into complex math into actionable policy insights. So by moving beyond the black box, we enable our national agencies to not only predict disasters, but also understand the underlying drivers. So this transparency is the foundation of resilience resilient AI assistant disaster management infrastructure for Sri Lanka. That's what we believe. So for the conclusion, as we reach, in this presentation, the message is very clear, I think. The technology to protect Sri Lanka from climate-driven disaster is no longer just a research concept. It is a proven reality, because people can do research, but we have to act upon it. We have validated these models not just in the lab, but across the Mahavali, Malwatu, and all these geographical regions, even in global basins like Narmada, in Japan, in Vietnamese rivers, and so on. So we have shown that a cascaded model also has like 21% accuracy than standard industrial model. So I want to remind that we introduced cascaded analysis in 2021. Now it's been 5 years. Within these 5 years, there have been more than thousands of new algorithms, which is much better than these models. So this means more time for evacuations. Like if we can predict, we have more time for evacuations, more precise reservation management, and significant reduction in the economic losses. But also, the accuracy alone is not enough for national policy. We understand that. We understand for an agency like DMC is to issue a red alert, they need to trust why behind this data. So this is why we have like explainable AI. So it gives like waterfall of evidence to showing exactly how rainfall, temperature, and terrain features are interacting to create a risk. So we are building a bridge between data science and industrial trust. So the third one is like a common misconception is that like AI requires supercomputers that we simply don't have. I have though. But our research proves that opposite, because we always try to reduce the computational complexity, choosing the different like efficient machine learning models like LightGBM, XGBoost. We have created system that is light enough to run on a standard department hardware while remaining heavy enough to capture the complex climate patterns. We also don't have much data, right? So with less data, we cannot actually run huge models. It's kind of an advantage. So this is a framework tailored specifically for Sri Lanka. That's what I believe. For current infrastructure designed to be scalable from one river basin to entire island until we have supercomputers. So finally, we often say like we lack perfect data to make decisions. We cannot wait for that. But climate change is not waiting for us to find perfect data, right? So the flood, the air quality crisis, the energy blackouts are happening right now. So my final message is that we have the intelligent systems, we have the validation, we have the transparency. It is now the time to move from awareness to action. By integrating these predictive frameworks into our national infrastructure, we can actually stop reacting to disasters. We can stop reacting to disasters and start predicting them. So let's ensure that the next storm, we aren't just prepared, but we are actually ahead of it. So thank you very much. That's all from me. I'm not sure if I took enough time or more time. And if you have any questions, you can always contact me here or right now.
Thank you very much, Dr. Namal. So we will go into the Q&A session. So suppose first question from myself actually. So as you discuss, right now we are experiencing about lack of quality data. So you maybe know both we have studied in Japan. So in Japan, it is available free data, quality data, and without any hesitation, they are giving the data for the researchers. And even though they have the responsibility for their data. I think, am I correct, Dr. Namal? Yeah, they have a responsibility. But in Sri Lanka, so I was also experienced when I was doing my masters. It was a very serious case. I had to develop a climate change model based on statistical downscaling and dynamic downscaling. So after purchase the data, then I was experiencing about missing data, and trend is not following the set trend, and those were the cases. So how do you integrate this machine learning to fill this gap? Machine learning and AI to fill this gap, because even though from the very recently completed project called Dam Safety Water Resource Planning, so they have initiated the budget through the World Bank to install autonomous climatology stations, real-time station. Right now, it is not functioning. So after project finish, then there are no continuation for the maintenance of the stations. Nearly 127 stations have been installed within the entire country. I think you maybe also don't know about that. So I had access to that system when I was working in Mahavali. So I also observe that system is right now not functioning, because I just want to know. Right now, I am doing some study to develop in-house autonomous system to our campus premises to integrate the climatology data in this Paduk area, and then store it real time to a computer, to a database, and then do the predictions only for this area, and try to assimilate a regional climate model for the downscaling. So I need your input. How can we integrate this machine learning and AI to fill this gap? That is my question. I think Professor Upaka, you have an answer.
Yeah. Now, if you look at the data quality, if
Yes.
like the observational data, we definitely have missing data. Not only in Sri Lanka, but also in all other countries.
Yes.
Even here, we have missing data. For some of my my recent work, which is going in Ireland, we have free access to all data. We don't have to purchase anything.
Yes.
So it's readily given to anyone. I mean, not only for research, but also for any commercial activities they can get. But again, so sometimes we find some missing data in these data series. So you
Yes.
can definitely fill these missing gaps. That is possible by looking at the trends and so on using machine learning algorithms. That's one way of doing it. But if you go back to the physics, you definitely can. Now, for example, rainfall data. If you have the rainfall data, missing couple of rainfall data, you can go back to the basics and like normal ratio methods, or you can go to different physics and you can fill it. But I would like to highlight something else. Now, if you particularly look at climate data, you can get satellite data. You can get
Yes.
model data. But the issue is, even though these data are freely available for most of the cases, like for example, if you want Sri Lanka, you can get a grid. You know, we have 550 plus rain gauges in Sri Lanka under Department of Meteorology. But again, if you're not rich enough to buy, for example, myself, we bought some data, but we are not rich enough to buy all things because it's so expensive. Now, what I would do is I would identify several important locations using the grid system. So then I go to the models and I will download these data. Like for example, you can have loads of data from satellite images and so on. But again, can we trust them? So you can go to the bias correction and correct these satellite data and get into the flow situations and so on. That is very possible. You can even drive machine learning algorithms to do that for you.
Yeah, I mean, actually, so I have observed, especially the data that I was purchased. So I mean the field the people who are working at the field, so they have replaced a couple of data by using the existing data. I think maybe you have the experience after visualizing the existing trend line, so then we can find out kind of cases like this. So that's why I just wanted to know how to omit this kind of it is kind of a bad behavior actually, cooking the data. So that is very common. I mean, I'm openly saying that, not targeting anyone else, but that is very common in Sri Lanka, especially for the um, meteorology data. So so for this,
Yeah, data massaging is there. Data massaging is
yes,
some people do
yes,
that, but again, you can find them. You can easily
yes,
find them. Now, for example, if you go back to the basic theories and so on,
yes,
and if you look at the time series, you can easily find them.
yes,
If someone has massaged the data, that is easily found. Yeah.
yes. So then another question. So right now we are focusing about prediction. I mean, we have talking about prediction, how to use the AI and ML to have a strong predictive model to enhance the disaster preparedness. So like in Japan, so even if suppose if earthquake comes, at least before 20 seconds we are taking the um, information. It's like an alert, ne, Dr. Nama?
Yeah.
So I was experiencing, it was a very near death experience when I went to Niigata 2024 January 1st. The same day, Noto Peninsula tsunami came. So it was a good experience for me, how they have reacted against to, I mean, to evacuate the people who have suffered within that region due to that disaster. So we don't have such a strong protocol. Even still, we don't know about the number of fatalities and what happened. So how can we integrate these? I mean, social matters over the AI and ML, then goes to a engineering solution uh, by strengthening the model using observed data. So how can we, because this is in terms of one of the question what I received from one of our student. So he wants to develop a model uh, to capture the existing trend line, then predict the disaster, and then give information to the society. So you may have to have a some preparedness, like in yes,
We had this idea, like
yes,
we did one prediction forecasting for Kalani River,
yes,
which is like every year, it is
yeah,
flooding.
it is
Whatever
flooding.
you do, it's gonna flood. So we had this idea, and me and Professor Hoshino, who is my PhD supervisor, when I was doing my PhD, like the model we did is really good. It's predicting like perfectly. So I suggested, what if we do this as a project for Sri Lanka, but we don't have the catchment
Yes,
data that we need, because we need the catchment from the basin, right, where the rainfall is happening, but we don't have much. So what I proposed is, like, if we can get a good grant, we can develop
our
the
own model.
stations, and
Yes,
then
our own.
maybe we have an agreement, we can have an agreement, we can have a discussion with the government, and then we can plant these stations, because our model is good. We just need the data, real-time data, because we can actually predict 1 hour, 2 hour before, like what's going to happen in the flooding area.
Yes,
So the problem is, like, we could not do that because we did not get a grant. And when we try to come, actually, me and Upaka sir and also Professor Hoshino from Japan. Like we all came to Sri Lanka and tried to talk with disaster management center, and then we could not. So we had this clear idea what to do, but yeah, that's where we are. We can implement these things. It is possible. We
Yes.
need.
But
Yeah,
we
on
don't
top
have
of
any
that, on
backup
top of that,
support.
Charitha, I just would like to add something now. What is happening in the world now? Sometimes you probably heard about this catchy phrase, citizen
Yes.
science. Now, people involvement in data capturing. Now, I'm
Yeah.
not saying that we can't trust Sri Lankan people. I mean, for data capturing. Okay, so what some other countries do at this moment? So they probably say you have a staff to measure the water level. Okay,
Yes.
so people just see that and they just text it. So they have a small app developed and they text it. They just feed that value. Or they even take a few photographs and they do it. So it'll automatically come to the data servers and they'll capture these data, real-time data. So these will be used in some countries to run the models and give the prediction exactly and so on. So it's like the people who engage in the policy development and so on. So that is happen in the world at the moment.
Yes. Another question. So right now, actually, I'm doing that. So one of our research group is carrying out a research for the drone-based survey. They are capturing large number of images using videos and then segmenting those lengthy videos for the large number of images, like more than 50,000, 100,000 images. Actually, when the Ditta storm came, we have identified our majority of structures are not capable to handle such kind of a severe flood, especially the railway bridges and road bridges. Some of the bridges, retaining walls, and everything has been collapsed, and the buildings have collapsed, and river path has been rerouted. So these kind of several scenarios. So I just want actually some idea to implement this. So in terms of monitoring the health of the entire infrastructure, to give a warning or categorize. So suppose even if we take as an example Nuwara Reservoir, which is located near to the base hospital in Anuradhapura. So in 2010 and 11, due to the severe flood, they have gave a warning to the hospital if Nuwara embankment broken, then you will fall in a serious matter. So you want to evacuate. So then they have rerouted the water path and then send it to the Malwathuva. Similarly, in the following Ditta storm, from Nachaduva towards Nuwara, there is a feeder canal. So they have cut the feeder canal embankment and rerouted the water pathway to reduce the volume of water transferring towards the Nuwara. So suppose if we can have a large database based on the images and LiDAR data, so then we can give them a at least time plan how to maintain your structure, how to I mean whether it should be demolished or whether it can be reconstructed or do some remedial works to get the original strength. I mean, suppose to extend the lifespan. So I need kind of your idea. So how to integrate the decision support system powered by the ML to enhance the output of this kind of research.
See, Charitha, the first thing is if you are thinking about satellite drone images, now you need to be
Yes.
very careful of getting permission. In Sri Lanka, I think you have to get
Yeah,
the
yeah. Yes, I'm
permission from the
suffering from that
president.
one right now.
Yeah,
Yes.
from the president office to get fly a drone for research purposes and so on. Then the next thing is suppose you are getting drone images and so on, and you can develop them during the say stormy periods. If you can capture them to during the stormy period, definitely you can run them to the
Yes.
pre-trained model and say that these are the guidelines. For example, just like the drought scenarios which I told you earlier in my presentation, you can develop those things, and you can even develop maps for that. But I would slightly go ahead with that. Sometimes you are not capable of capturing these drone images during a heavy intensified rainfall period.
Yes.
The good thing is in Sri Lanka, I think India recently started a new satellite imagery service, which you can get to 2 meters into resolution, I think, and it is
Yes.
freely available if you
Yeah,
register with them. So India is freely giving satellite data to Sri Lanka if it is registered. I can't really remember the name, but
through the IITM, Institute of Tropical Meteorology. Yes.
yeah. So I can't really remember the name of the satellite, but they are giving 2 meters of resolution. That's one of the best. Now, even if we don't have that, every 4 minutes we are captured. Every 4 minutes interval, we are captured by a satellite in the world. So
Yes.
we can't get them, like, for example, Sentinel, Landsats, and so on. We can't get all of them free of charge, even though we get free of charge images. Sometimes we have to deal with cloud cover and so on. These are mattering factors. But again, we are captured. At this moment, we are captured. The issue is we can't get the maps freely.
Yes.
Because we don't have country-wise agreement with NASA or with some other Japanese satellites. So easily what we can do, I believe we have one satellite over Sri Lanka from Japan. So we can have an agreement with Japan and we can get the free images. It has to be like country-wise agreement.
Space agency. So,
Space agency. I think it is right above Sri Lanka.
Yeah. It is exactly above the Sri Lanka.
Yeah.
14 kilometers.
So we have everything there, but the thing is we don't really have a connection to them to it may be just a letter to write to the particular people in Japan and saying that let's come to an agreement for research purposes and so on. Because Sri Lanka and Japan has lot of like positive collaborations, so they can do that easily. So if that is done, so we probably can get 5 to 10 meters resolution data.
Yes, thank you, sir. So one last question. Actually, how can predictive modeling help to long-term risk planning, and how machine learning play a crucial role in social media analysis? Suppose people may share some fake news in terms of the actual information. So likewise, we want to, to minimize the trauma. So this webinar series have been started from that one webinar to address the trauma after a disaster. So then even we can deploy the machine learning to capture such kind of falsify information through the social media, and then we can integrate that predictive and predictive model results to help in long-term risk planning. Is it possible?
It is possible. It is kind of another kind of project, right? The machine learning project that we can train. Yeah.
So I actually I hope to initiate this kind of work. So if possible, kindly give some contribution.
Yeah.
Yes. That is actually, so you maybe know Dr. Namal. So if something happened in Japan, they are very careful to bring that news to the society, to handle the trauma. So even if when I was in Saitama University, just 100 meters away, Arakawa River, that is one of the largest in Japan, severe flood came. They just gave us a warning, and they have evacuated us to the Saitama University. That was our evacuation, the shelter. So that's all. They didn't come and did the videos and put into the
That's
social
the
media.
thing. Maybe
Yes,
the problem is with our society, right?
yes,
Because the Japanese people, they don't trust the social media because
yes.
they have a good government, they have clear announcement systems, and that people believe.
Yes,
They
people believe
always
that.
follow. They
Yeah,
always
you
follow
maybe know
what
if they say at 10 a.m. it's snowing, then actually
it's
10
gonna
a.m.
snow.
is snowing.
Yeah.
We have to bring the umbrella. So anyway, thank you very
that's
much for your kind contribution. Especially I would like to thank Professor Upaka, Rathnayake and Dr. Namal. Right now, maybe
Charitha, I think one has raised the hand. Ajit.
yes, please. Who is Mr. Ajit? I think no, sir.
It's gone. I think it's gone.
Yeah, it's gone. It's gone.
Yeah.
So thank you very much.
On top of one little thing, on top of what
Yes.
Namal said, and he said, so the people have the responsibility.
Yes.
Now people should act responsibility. I know everywhere we have like, how would I say, nuts.
Yes.
It's there. Not only in Sri Lanka, but also in Ireland, but also in Japan. It is
Yes.
there. But we have to trust the system, because the trust has to be there from the system to us as well. So this is where the people's responsibility comes into the action. So
Yes.
not believing what others says. Go with the scientific facts and so on. But the issue is, Charitha, sometimes even the professionals bring fake
Information,
news,
yes.
probably to get it popularized or whatever the reason, not only in Sri Lanka, but also here in Ireland, I must say. So people, even the professionals, bring these fake news. Like, for example, if I don't want to take any cases because that may go to someone else and so on. I don't want to make this. Suppose you have a crisis. So people will come and talk about that particular crisis, saying that, okay, suppose he or she is a PhD holder and so on. So we believe, people would believe he's an expert, but his PhD may be in somewhere else, some other area, some other discipline. So still they talk and so on. People, the generic public, might think that okay, this guy, he's this professor, this doctor, or this guy is talking about this particular thing. This should be correct. But if it is not correct, now eventually the trust to these professions will go away. That has happened. That has happened for some time.
Yeah, thank you very much. And thank you very much, Dr. Namal. Right now, I think it is around 1
It's late night for him, I think. Maybe early morning.
It's
yeah,
1
around 1 a.m. So 1 a.m. This is usual for the scientists who are working in Japan. This is normal. So anyway, thank you very much, and thank you very much for your valuable insight. And I will contact you in future.
Yeah,
Both
Charitha,
of you.
in case if someone wants to collaborate and so on, we are open. Namal and
Yes.
myself, we are very
actually,
much
sir,
open.
Actually, I just want to develop a system to handle that. The capture the social media and integrate that actual prediction values. Then it will brings to the society as a correct information. Then we can handle the stress and trauma. So later we will discuss how to integrate the available information. Okay, so thank you very much.
Please pass the emails to anyone if it is interested.
Yes.
Yeah, we are happy to.
Ms. Umyangana, over to you. Thank you very much.
Thank you.
discussion, Dr. Charitha. And once again, I would like to thank Professor Upaka Rathnayake and Dr. Namal Rathnayake for engaging with such an insightful conversation as to how machine learning can actually bring us to a closer to see what kind of an impact that these climatic changes would be in the prospective future. So thank you very much for those insights. And also I must appreciate your commitment in joining this, despite the fact that you are joining from different time zones. I really appreciate you joining and engaging with this insightful discussion. So thank you very much once again, Professor Upaka and Dr. Namal for joining. And I believe that you would be constantly in touch with SLTC and in future collaborations. Thank you very much. And with that, I would also like to invite all the participants to join with the next webinar that we would be conducting tomorrow on fire and safety structures during disaster. This would be happening via Zoom from 7 to 9. And this would be conducted by Dr. Pasindu Veerasinghe from the Department of Civil Engineering at University of Moderator and Professor Chaminda Bandara from the Department of Civil Engineering and University of Peradeniya. And the session would also be moderated by Dr. HMST Herath from the Department of Engineering at University of Moratuwa. So with that invitation to everyone to join the webinar tomorrow, we would now conclude the session for today. Thank you very much, everyone, for joining, and have a good night.
Thank you very much.
Thank you.
Okay, bye-bye then.
Very much.
Thank you very much
Yeah.
once again.